5.2, we're going to look at the concept in differential equations known as slope fields. Specifically, what are slope fields and why are slope fields so useful for us? So what are slope fields? Okay, so let's say I have a solution to a differential equation, capital H of y equals capital G of x plus c, okay? So this solution actually represents an infinite family of solutions, as different initial conditions will lead to a different value c and hence a different particular solution, okay? So going through all of these solutions and analyzing the behavior by choosing a different c value each time can be quite painstaking, okay? So if we want an easier way to analyze the behavior of these solutions, like let's say what the concavity of solution is, where solution increasing and decreasing, what is the end behavior of our solution, instead of solving for all these infinite different values of c's and comparing their solutions, what we can use is we can use a differential equation to evaluate the derivative and hence the slope of the tangent line of our solution at specific points. Okay? So these slopes can be plotted to visualize and analyze different solutions of the differential equation, giving us a slope field for different solutions of our differential equation. Okay? So as a result, one can trace through the initial condition to identify the solution curve to a particular differential equation. Okay? So as a result, we can determine the different properties, concavity, increasing, decreasing, and end behavior, all that's good stuff, for many different types of families without having to go through plugging and chugging different c values or without even having to solve our differential equation. So if we have a differential equation that we don't know how to solve because it's too difficult or because we can't use separation variables, we can plot a slope field from that differential equation and visualize what the solutions to those differential equations look like for different initial conditions. Something that's very, very, very useful and time-saving and efficient if it's not worth the time to try and grind out a solution. So for an example at right, for initial condition of x equals 0, y equals -3, the black curve is the solution to our differential equation. Okay? For an initial condition of x equals 0, y equals 2, okay, we can see that this red curve is our differential equation, solution to our differential equation. So as a result, we can see that different initial conditions will lead to different values of c and hence a different particular solution, and hence different types of behaviors. Okay, so this is why slope fields are so useful for us, because they provide us a qualitative measure of what's happening with our differential equation and what's happening with our solutions, as opposed to a quantitative measure. So generating slope fields. To generate a slope field at a point x naught, y naught, all one needs to do is use a differential equation to evaluate the derivative dy over dx at that specific point. The specific numeric value of the slope at a point cannot be plotted, okay? So if you have like -1.22222, that's a little bit difficult to plot. So the following keys are useful for sketching. Zero slopes are going to be horizontal, aka horizontal tangent lines. A slope of 1 is going to be oriented at 45-degree angles. Positive slopes will point up and to the right. Negative slopes will point down and to the right. Okay? Let's see here. So, and then in general, you can plot the steepness of your slopes based on the relative values you get for the slope of each at different x and y values. Okay? So let's take an example where look at an example right here. So for example, the differential equation of dy over dx equals x minus xy. The differential equation of the slope field we looked at in the prior slide has the following slopes at x equals 0, y equals 6, and x equals 1, y equals 2. So at x equals 0, y equals 6, we get dy over dx equals 0 minus 0 times 6 equals 0. So at this point, that tells us the line segment sketch will be horizontal and appear as such. Okay? So we know that we're going to have a horizontal tangent line for our differential equation, and our solutions of our differential equation at x equals 0, y equals 6. Okay? At x equals 1, y equals 2, dy over dx is going to be equal to 1 minus 1 times 2, which equals -1. So line segment at this specific point is going to point down and to the right at a 45-degree angle. Down and to the right because it's negative, and at a 45-degree angle because it's 1. Okay? Note here that this is useful, that we can determine what the tangent line, slope of the tangent line is, and we can determine actually where we have horizontal tangent lines at without solving this differential equation, which is a very, very useful tool for us. Okay? So analyzing properties of solution curves, okay? So using a slope field in the corresponding differential equation, the following properties can all be determined without ever solving the differential equation. End behavior in horizontal asymptotes, increasing and decreasing intervals, and concavity, okay? So for example, right here, if we look at this slope field right here, we can see that the limit as x goes to plus or minus infinity of our solution of our differential equation is going to be 1 because we see that our solution plateaus at y equals 1. We can see that we're going to be increasing, we can see that we're going to be decreasing from negative infinity to 0 for the black curve, okay? And then we're going to be increasing from 0 to positive infinity for the black curve, from 0 to positive infinity for the black curve with a local minimum at x equals 0. Okay, perhaps where I said not the black curve, but any curve that is any curve that occurs for y less than 1. Okay, we can see that we're concave down from negative infinity to negative 3 over 2. Okay, for all curves for y less than 1. And then we can also see we're concave down again also from about 3 over 2, aka about 1.5 to positive infinity. And then we can see we're concave up from about negative 3.3 over 2, aka negative 1.5, to 3 over 2, 1.5. We can see we're concave up here. Okay, so this is for solution curves for y less than 1. Okay, for y equal to 1, we get the green curve, and then for y greater than 1, we see that the properties become inverted. Where we're concave, aka where we're concave up, we're concave down, and where we're increasing, we're now decreasing. Okay? So we can see that the initial condition influences the above properties of a particular solution y equals f of x. So let's take a look at end behavior. So the key with end behavior, okay, if we're not given a slope field, we can still determine it from a differential equation by taking note of the fact that the slope field plateaus at a horizontal asymptote. So as a result, as x goes to plus or minus infinity, dy over dx is going to approach 0. All right? So we're going to set our differential equation equals 0. We solve for y to determine our end behavior. So in this case right here, we have the limit as x goes to plus or minus infinity of dy over dx equals 0. Okay? So that tells us x minus xy, the differential equation that we're working with here, is going to be equal to 0. So we can solve this equation for y. We separate it out. We get x times 1 minus y equals 0. So we get 1 minus y equals 0, or y equals 1. So that tells us the end behavior of our differential equation is going to be as x approaches plus or minus infinity, f of x will approach 1, which is what we see happening right here. Increasing and decreasing intervals. So recall that increasing intervals occur if our derivative is greater than 0, and decreasing occurs if our derivative is less than 0. So we're going to set our differential equation to the appropriate inequality and solve the inequality. Okay? So for increasing, we're going to have dy over dx is greater than 0, which is going to be x minus xy is greater than 0, or x times 1 minus y is greater than 0. Okay? So in this case right here, we have to be very careful because what we can take note of here, okay, is that if x is greater than 0 and 1 minus y is greater than 0, then we're going to have positive times positive, which is going to be greater than 0. But if we have x less than 0 and 1 minus y less than 0, we're going to have a negative times negative, which is also greater than 0. So we have two different cases we have to consider. In case 1, we can set x greater than 0, so x is going to be positive, okay? And 1 minus y will be greater than 0, aka 1 minus y will also be positive. So that tells us, solving for the second inequality, that y is going to be greater than 1. So we're going to be increasing, okay, if, y is less than 1. So we're going to be increasing if x is greater than 0 and y is less than 1. And then in case 2, where x is negative and 1 minus y is also negative as well, we're going to have x less than 0, aka x is negative, and we're going to have 1 minus y less than 0, aka 1 minus y is negative as well. Okay? So solving for this inequality right here is going to give us 1 is less than y, or our differential equation is going to be increasing if x is less than 0 and y is greater than 1. So we have our conditions for increasing and decreasing with this differential equation right here. Now, if we're decreasing, we set our differential equation to less than 0, which is going to give us x minus xy less than 0. And again, gives us x times 1 minus y is less than 0. And as a result, we're going to get, what we can take note of here is that if x is negative and 1 minus y is positive, the overall expression is going to be less than 0 because a positive times a negative is, or a negative times a positive is negative. And then right here, we can also take note that if x is positive but 1 minus y is negative, then positive times negative will also be less than 0 as well. So as a result right here, we can focus again on two separate cases. Case 1 where x is less than 0, aka it's negative, and 1 minus y is positive, aka it's greater than 0. So we set x less than 0 and 1 minus y to greater than 0, which is going to give us x less than 0, y greater than, or 1 greater than y for decreasing. And then case number 2, we can set x to positive or greater than 0 and 1 minus y to negative or less than 0. That gives us x is going to be greater than 0 or y is going to be greater than 1 for decreasing solutions. So solutions are decreasing if x is less than 0 and y is less than 1, what we got right here, or if x is greater than 0 and y is greater than 1, what we got right here. Similarly, for concavity, we can recall that an interval is concave up if our second derivative is greater than 0 and concave down if the second derivative is less than 0. So we're going to differentiate your differential equation to obtain dy over dx, or to obtain your second derivative, and you're going to set the expression equal to, or you're going to set your expression to the appropriate inequality. Then you're going to solve the resulting inequality. We're not going to go through an example with this because the example of differential equation I have chose tends to be quite difficult, whereas the examples on the AP exam tend to be more straightforward because they test for concepts as opposed to rote calculations. Okay, so we'll take a look at some more examples in class with concavity.